Okay, our next speaker is Charles Dismukes. So let's go.
Thank you, Mike. It's a pleasure to be here. I've recently arrived as of August 1st, and after having spent a career of more than 25 years just down the road at Princeton University. It's been a very exciting 3 or 4 months thus far. I'll share with you some of the proposals that I've worked on since coming here. And the area that I work in is described here. It's renewable energy science, working in both the microbial energy production side as well as in the chemistry side of making catalysts for water splitting. I noticed many people spoke about their training. I'm actually trained as a chemist, as an undergraduate at Lowell Technological Institute up in Massachusetts. Trained in physics and chemistry in my PhD work at University of Wisconsin in Madison, and then on to Berkeley to the Calvin Laboratory where I learned some biology as well. I still consider myself, however, this is my alternative profession. My first choice was that of an astronaut. I grew up in the Apollo era, and but plan B was to become a scientist, and not just a scientist, but a chemist, because chemists have that other attribute that goes beyond merely observational science to create new matter that didn't exist before. And that was the frontier to me, if not in space, at least in the lab. So I'm going to actually make the mistake of choosing only one of these two areas to talk about. I'll talk about the chemistry side. The work that we do in microbial metabolism is probably 2/3 of the lab work that we actually do in terms of current horsepower of people. But nonetheless, I think 10 minutes doesn't allow us to do justice to all. I'll come back to the biology later to the end. So here's the slide that depicts the renewable resources. We all know that our future is going to be dependent upon developing these resources. And you can see here our world energy current usage is on the order of 13 trillion terawatts, rather. And the resources that are available are essentially biomass, geothermal, and solar for that. So you can see there's a lot of activity in those three areas for developing renewable energy. Global use is largely 2/3 fuel, 1/3 electricity. So that tells you want to make fuels. You also obviously want to use the sun to do that as the most abundant resource. And that suggests in terms of renewable fuels, you want to make hydrogen. So if you want to make it renewable, you're going to have to make it from an abundant resource that can be regenerated. That would be water. That 13 terawatts of energy would require about 1 Olympic-sized pool to be burnt or converted into hydrogen and then used to make energy. And the nice thing, of course, is that you would regenerate that pool full of water at the end. So that is the goal. Chemists think about that problem in terms of energetics. This is the energy diagram showing the free energy of water relative to the free energy of the oxygen and hydrogen products that you would have to make. This turns out to be a big energy difference here. That's why there's so much water and why it's so difficult to split. If you wanted to do that reaction and not use a catalyst, you would have to break 4 OH bonds. That would be about 119 kilocalories per mole. Hard to judge what that is for non-chemists, but effectively to make the reaction run at equilibrium, you'd have to create about 2,500 degrees centigrade. Effectively, there's no reactor that exists that could tolerate those kinds of conditions. So hence the need for chemists. Chemists try to figure out ways in which to overcome that barrier by having somehow weakening the OH bonds and forming the oxygen-oxygen bonds simultaneously. Still mechanistically complex, 4 bonds to break, 1 to make. Very, very tough metrical constraints. That's why chemists are abundant on the planet of the Earth. Tough chemistry. The best known catalysts are noble metal catalysts, platinum, palladium, essentially 10 million times less abundant than the kinds of materials that we want to use, and very, very costly. And even those have about half the energy of this gap here must be provided in excess to overcome that. So the activation barrier is very, very high still, even for noble metal catalysts. The way to do that, of course, is to break that up into little segments of energy gaps on the way up, if you can. That's the way enzymes do it, and the way chemists like to try and design catalyst to do that. A simple metaphor for that would be a fish gate, whereby you're going from a low potential energy to a higher potential energy site, and you do that by means of a ratchet of smaller energy increments. And the fish gate is the mechanical device which allows the fish to go in one direction and retards its motion in the other direction. That's exactly what an enzyme does. And so what is the molecular counterpart of that? Well, photosynthesis does this by an incredibly complex enzyme called the photosystem II water-splitting enzyme that arguably has anywhere from 19 to 26 subunits. And at the core of that is an inorganic cluster depicted here in atomic resolution, which has that composition. It has 4 manganese atoms, 1 calcium atom, and oxygens that bridge this together. We call this a heterocubane with calcium and manganese in the core, in this cubical core, and then a dangler manganese. So that's the target that we're after in making. Now, nature actually uses this same identical core in all of the oxygenic phototropes. The cyanobacteria and the algae that Debashish was telling us about evolved somewhere about 3 billion years ago. So these were the original oxygenic phototropes, and they persist today, along with the higher plants from which evolved from them. But the same inorganic blueprint is adopted by all of those. So this is a remarkable conservation. Nature has been able to find one solution over 3 billion years, roughly 1,000 times more than necessary to evolve every enzyme in your body effectively. So there is a tremendous lesson here about nature's blueprint is special, and that if we don't learn from that, we're really not using our heads very well. So what we've been attempting to do is replicate that system, and we have done that in an inorganic cluster that's depicted here. This is just the core of that. And as you can see, it shares some similarities, but lacks the calcium atom in that. And that has to be then tethered to a system that can allow light to absorb light, to do charge separation, remove electrons from that cluster, and turn the electrons over to some external circuit, a photovoltaic circuit of some kind. That's exactly what the photosystem does. And the way we have done that is to make complexes that have that central manganese oxygen core as depicted here. Now, there are other organic components that are needed to assemble that, and that's the magic of chemistry required to pull together such a complex device. These turned out to be very interesting molecules. They were actually the first transition metal oxo cluster in freestanding molecular unit that was known. Lots of examples of extended solids, but no molecular clusters of this type were known until these first appeared about 10 or 12 years ago. So if you take these and you put them into a proton-conducting membrane called Naphion, and that's the chemistry of Naphion here, Naphion is used in fuel cells as the magical membrane which separates the proton-reducing side from the water-oxidizing side, or I should say the oxygen-reducing side of a fuel cell. And so what we're trying to do is build the reverse of that, which is a reverse fuel cell that splits the water, making hydrogen and oxygen. And that was successful, actually, by taking these catalysts, putting them into a proton-conducting membrane, and attaching that to an electrode here. And once that electrode is there, you can inject electrons into that and observe a photocurrent that produces, in this case here, oxygen by this reaction here, protons accumulating in solution. That system works very nicely for thousands of turnovers. You can do the next step, which is to put that into a photovoltaic device, and that would be a device that has then the capability of absorbing light by a separate chromophore, ruthenium in that case, doing charge separation and using that light to do the charge conversion and using our catalyst here to convert that into stored free energy of oxygen and release of protons. So one can actually use a photovoltaic cell to do the light absorption and the catalyst here to split the water. So certain attributes of the natural photosynthetic system can be recapitulated here. This is a rather inefficient catalyst by comparison with nature's catalyst, probably 1,000 times slower turnover or thereabouts. And so there's lots to be done to improve it, to make it a commercial device. But at least we're away from those noble metals that occupy the rarest position on our Earth and high cost, as you know. So in terms of this other side of what we do, is probably best represented by the number of proposals that I've been involved with since arriving at Rutgers. This is an incredibly stimulating environment. I have written, or will have written, 5 proposals by January 15th, if everything works out well, and host a site visit from Toyota R&D tomorrow. And that all involves Rutgers people. So there are 2 DOE grants, 2 NSF grants. I think Debashish mentioned already the collaboration on algal biofuels with the Falkowski Lab. This has all come about through the Rutgers Energy Institute. There's an NSF proposal with Michael Vogelius and Youngju Lee in the mathematics department and Martha Greenblatt in chemistry. And so those involve solar initiatives through the NSF. The DOE involves photosynthetic efficiency grant with a consortium as well. And also there's another DOE grant on precisely these catalysts here, which I'm learning that there's a lot of interest here at Rutgers in the material science side of things, working with Dunbar Burney and people from the engineering school, Monsef Tayahi, on projects as well. So it's been a very rich and stimulating environment. Let's hope some of these grants come to fruition and we'll be able to work together.
Okay, thank you very much.